Okay guys, we are going to talk about terminating systems and how we can simulate terminating systems. So the first thing we have to find out is that what is the terminating system? What is the definition of terminating systems? So basically systems such as barber shops, restaurants, supermarkets, those are the ones that we are calling terminating system. What does that mean? That means this system works for a specific number of hours every day. They close at the end of the working hours. They don't let any new customer to enter the system, but they continue working till everyone who is in the system is out, and then they close the system and they are done for the day. So when we go to the start of the system and the next morning, we always start with 0 customers in the system. Okay, so terminating systems always start with 0 customers in the system at the start of the simulation, always continue working for a specific number of hours, and after they are done with the working hours, they close the door. They don't let any new customer to come in, but they continue working till anyone who is in the system is out, and then they stop the simulation. Okay, so the 3 main conditions of the terminating system have been specified here. We are working for a specific number of hours. For example, in a barber shop, we may work for 8 hours. Okay, or in a restaurant, we may work for 8 hours and then we are done, we close the door. We don't let any new customer to enter the system after the working hours are over. Okay, however, we continue working for a little more time till everyone who is in the system gets the service and leaves the system. That's when we stop the simulation, we stop the system, and we are done. Okay, so that's what we call by a terminating system. Now let's see how we can potentially simulate a terminating system. So the system that we are going to simulate is a restaurant. So it's a simple system. So this restaurant is a terminating system because this restaurant is working for 8 hours a day, and after 8 hours they close the door. They don't let any new customer to come in, but they continue working till everyone who is already in the system gets the service and leaves the system. So this simple restaurant is composed of 3 locations. The entry where the customers get enter first, and then the order queue when the customers wait to place order, and then the clerk where the customers place their order, they pay for their food, they get their food, and they leave the system. Okay, so for the in terms of the capacity of the locations, just make sure that entry and clerk have capacity of 1, and order queue has capacity of 4. Only 4 people, maximum up to 4 people can wait in the order queue. And also make sure your queue is a queue and not a conveyor, and also make sure that the queuing rule is first in, first out. Again, none of these are really important for a terminating system. I'm just mentioning these specifications so that you make these changes in your model, so we can get similar numbers when we run our simulations. We get similar numbers because the details of the simulations are similar. So customer enters, so our only entity is the customer, and the customers enter one by one, and every 6 minutes exponentially distributed. Okay, so that's what we have basically for our customers. So customers enter through entry point, they enter one by one, every 6 minutes exponentially distributed. So our only entity, that is customer, will enter the system through entry one at a time from the start of the simulation, and the inter-arrival time is 6 minutes exponentially distributed, and our occurrence is infinity, meaning that for as long as we run the simulation, customers can enter the system. Okay, so that specifies the arrival of customers in this simple example. Okay, so now let's see how we can model a terminating system. Okay, so let's go to processes. So when customers enter these systems, where are they initially? So customer are at entry point, right? Okay, so what happens here? Do all the customers enter the order queue and go place their orders and so forth, or no? Some of them may enter, some of them may not enter. As I said, that in this system, the restaurant is working for 8 hours. After 8 hours, the working hours are over, and so we don't let any new customer to enter the system. So, okay, so what happens here is that when customer enters the system, either they will go to the order queue if we are in the 8 hours of working time, or they are not allowed to enter the system and go place their order or get to go to order queue if we are past the 8 hours of working time. Okay, so the customers either get to the order queue, so destination is either order queue, they get to the system to place their orders if there is a condition: clock hour is greater than or equal to sorry, is less than or equal to 8. Okay, so what does that mean? That means if the simulation time, remember clock hour is a function that is known by the simulation. So simulation already knows what this means. We don't need to specify any attribute, any variable, anything. Clock is a function that simulation understands and knows. So clock hour means return the simulation time in hour. Okay, so clock hours mean return the simulation time in hour. If it's less than or equal to 8, that means I'm within the 8 hours of simulation. Then let the customer come in and goes to order queue. Okay, so that's basically what this condition means. Okay, and then what is the other scenario is that I am past the 8 hours of working time, I am past the 8 hours of simulation, so I don't want to let the customer come in, the customer should just exit the system. Okay, so then I go to next line, customer goes to exit. Under what condition? If the clock of the simulation is greater than 8. Okay, if I am past the 8 hours of working time or 8 hours of simulation, I don't want to let any new customer to come in. Okay, so under that scenario, then I'll let the customers to not enter the system, so they are going to exit the system. So so just make sure two things. Make sure when you are putting the user conditions, you do not put any if. If will be put by the simulation automatically here. So don't put any if, otherwise you get error. The other thing is that make sure we don't have new block here. So both these lines are part of one block. If you create a new block, you will get error. Okay, so make sure to pay attention to that one as well. Okay, so customers get to the entry point based on this simulation time. If we are in the 8 hours of simulation, we let the customer to come in and place their orders. If we are past the 8 working hours, we don't let the customer to come in and they are going to exit the system. Okay, so if the customers come in, where do they go? They go to order queue, so that they already have gone to order queue, right? If they come in, they go to order queue. So next line, from the order queue, they go to clerk to place their order. And when they get to the clerk, so let's assume here when they get to the clerk, they are going to place their order, and we have maybe a bunch of things that we want our customers to do. So we want the customers to place their orders, and that's going to take exponential 2 minutes time. And they are going to pay for their orders. That's going to get exponential 1.5 minute time. And they're going to also pick up their orders. They're going to, and that's going to take exponential 5 minutes time. Okay, so it's just that happens in this simple example. The clerk is in charge of receiving the orders, receiving the money, and then preparing the pickup, and each one of these have a different time. If I could have told you that, for example, the whole process of placing the order and paying for the order and pickup, for example, take 9 minutes or 8 minutes, and you would just say wait E8. Okay, that's fine. If that's the information I gave you, you can write that. But if you have the time for every part of the work for placing the order, pay, and pick up, you can just write a couple of wait statements after another, and simulation just make sure the entity stays and displays for all these amounts of time. You can also use the / for just putting the comment that the first one shows the order time, the second one shows the pay time, and the last one shows the pickup time. Okay, so that's not a very like we have done examples similar to this many times. Okay, so after we are done with all the wait times at clerk, then the customer is good to leave the system. Okay, so now we pretty much have modeled the arrival of customers. So they come to the system. If we are in the 8 hours of simulation, they come to the system, and they go to order queue, they go to clerk, place the order, and they leave. So that part is good because it takes care of the fact that after 8 hours of working, we don't want to let any new customer to come in. But remember, the terminating system have another important condition, and that's that condition says after the working hours are done, continue working till everyone who is already in the system receives the service and leaves, right? So if you want to do that, so what basically we should do? So we have to definitely do not let any new customer to enter after 8 hours, but we have to continue working until all the customers that have arrived have left the system. Meaning that if I have a way to count how many customers have arrived to the system, and I have a way to count how many customers have left the system, I will stop the simulation as soon as number of arrivals and number of departures are the same. Okay, but I have to check that condition after I'm done with 8 hours of working. After I'm done with 8 hours of working, then I stop the simulation as soon as I know everyone who has come to the system has left the system. Number of people who arrive equals the number of people who are done. Okay, so to be able to do that, we can go to our variables and create two variables. One is going to be arrive. That one is going to count number of people who have arrived in the system, who have come to the system. The other one, I'm going to call it process. That one is going to count number of people that have been processed, have received their food, and they are done in this system. Okay, so I create two variables to count how many people have come to the system, how many people are done and have left the system, and I stop the simulation when these two are equal. Okay. So the next question is that where is the right place for counting how many people have come to the system? Okay, how many people have arrived to the system? You can potentially do it in two places. One is here when we send the customer to order queue, so that's where we know the customer has come to the system, or at order queue itself when we know a customer is at order queue. As soon as they arrive to the order queue, we are going to count how many people have arrived to the system. Okay, right at order queue, I can increase number of customers that have arrived to the system. Okay, so that count how many customers have entered the system. So entering the system actually means getting to the order queue, not to the entrance, because when they get to the entrance, we may send them out or we may let them in. Entering the system meaning that they have succeeded to enter order queue so that they can get to the clerk finally and place their order. Okay, so increase arrived right at order queue counts how many people have entered the system. If I want to count how many people have received the service and have left the system, the best place to do that would be to go to the clerk, and after the customer is done placing the order, paying for the food, picking up the food, and so the customer is done and is going to leave the system, here I'm going to increase number of process. Okay, so number of customers that are done processing and they have left the system. Okay, so here I'm going to count increase process. So then I count how many people have come to the system. I count how many people are have finished and have left the system. So then what we need to do is to come here in our first line, remember? So after we are done with the 8 working hours, after we are sure we are past 8 working hours. Right here, I need to check one more condition if I want to stop the simulation, if I want to close the doors of this restaurant. So right here in the move logic, I'm going to say if arrived equals to process, meaning that if number of customers that have come to the system equal to number of customers that have received the service and have left the system, then stop. Okay, so stop meaning that means stop the simulation. Again, stop is a keyword. The simulation understands these words already. We don't need to define it anywhere else. Stop tells the simulation that stop the simulation at that point of the time where this line is going to run. Okay, so this line will run in the simulation only if I'm past the 8 working hours. After that, I'll continue running the simulation and processing the customers that are already in the system till everyone who is in the system is out. Then I stop the simulation. And that basically takes care of the conditions we have to put in a system to make sure that it's a terminating system. First, do not let any new customer enters the system after a specific number of hours of working. Second, after those hours of working are over, continue working till everyone who is in the system is out, then stop the simulation. Okay, so now our system is good, our simulation is good to be run. Okay, so make sure to save your simulation, guys, as you go forward. So let's run the simulation and see what do we get. So one question here is that do I need to specify any simulation time? The answer is no, because the simulation knows when to stop exactly. After the 8 hours of simulation are over, the simulation stops automatically when everyone who is in the system is out. Okay, so let's run it. Okay, so here I ran the simulation once. So in these 8 working hours and maybe a little after that the restaurant has been open, overall 78 customers have left the system and they have been in the system for about half an hour. Okay, so those are the numbers I get. Now the other important question is that what if I ask you to tell me how many people have come to this restaurant in a specific day? Okay, let's say on a Monday. How many people have come to this restaurant on a Monday? Maybe the manager of this restaurant wants to know this value so that they know how many people they have to hire on a specific days of the week. So the question is that how we can find the answer, because if I run the simulation only once, that's just one specific day. That doesn't show that what happens overall in Mondays in all the weeks that we have in a year, right? So that brings us to the concept of replication. Okay, so far every simulation that we have run it once. That means one replication. But here in the simulation option window, we have another place for specifying number of replication, and this number is automatically 1 always unless we change it. Okay, so let's assume here we want to run this for 10 replications, meaning that as if you are collecting data for 10 separate Mondays and to see what is happening in every Monday. So in each replication, we will have a different set of random numbers. If we get different customers, we may process them differently. So each replication is basically as if like a new day, a new Monday for us. Okay, so here I'm going to run the simulation for 10 replication. Instead of just one replication, one day, I'm going to run it for 10 replications. Okay. And here you see when we finish the runs, it shows run 10 of 10. That means we had 10 replications and all of them have been run. Okay, so here what we get here, so these numbers are basically average. So as you can see, our total exit is 67.4. okay, it's not integer anymore, because you may say, how come number of customers that have left the system can be 67.4? This number should be integer, and that's correct. But what we are observing here is not the result of one run, is not the result, is basically the result of, or average of all those 10 runs or 10 replications that we have done. Okay, so basically as if I'm going to collect data for 10 separate Mondays of a restaurant, and then at the end the number that I'm going to report to my manager is going to be the average of number of people who have left this restaurant in these 10 days. So that's the number I'm going to report. I'm not going to just observe what happened in the restaurant in just one Monday, because that's one specific Monday. Maybe something has happened in that day. Maybe we get more people, maybe we get less people. That doesn't represent how this restaurant will work on Mondays. So if I want to give a reliable number to the manager, I have to collect data on more Mondays, and finally I'm going to report the average of this data I have collected on several Mondays. So here basically 10 replication means that I have collected data on 10 separate Mondays, and at the end I'm going to report the average of the numbers of these Mondays. If I want to report the total exit on the Mondays, I'm going to report the average of the exit on all these Mondays, and that's going to be 67.4. If I'm going to report how long they have been in the system, I'm going to report the average of time in system across all these 10 days or 10 replications for which I have collected data, and that's about 32.75 minutes. Okay, so here on the left, so we have replications. Okay, so here I have the option average, and that's why we see the average of all replications here, or I have the options of all. Okay, so if I pick all, what we are going to see here is basically all 10 replications. Okay, and for example, for the first replication I had 74 exits, for the second I had 70 exits, for the third one I had 55 exits. You see how the results of replications are different even in just one computer. So that's just because different replication use different stream of random numbers. That's why the numbers are different. So in your computer too, when you run the simulation for several replications, you will see how each replication is different from another, not only in terms of total exit, but also in terms of how long they have stayed in the system, and basically anything that you want to get out of the simulation results. Okay, so here basically we also see the results for every replication 1 to replication 10. Okay, so one important thing here is that, as I said, when we want to report the numbers, I'm not going to report the number for one replication or two replication. I want to report the results across all these 10 replications, right? So here in the statistics option on the left, if you click on the statistics, you have the options to report a bunch of things. So I want to report the average. So when I check average, you see average row is added here, meaning that average across all these 10 replications in terms of number of people who have left the system is 67.4. Average across all these replications in terms of how long they have stayed in the system is 32.75. So these are basically the average row is the one we want to report, not just one replication, not just two replications and so forth. We want to report the results, the average of the replications. But more importantly, we can also report confidence intervals. So I not only want to report the average on what has happened in the restaurant, but also I want to report how the numbers were different around the average. Like if I had numbers larger than average, like 72, 81, and so forth, how far they were from the average. If I had numbers less than average, like 60 or 55, how far they were from average, how much they were less than average. Okay, so I want to get a sense of variability around average as well, and that can be reported by confidence intervals. So here we have the option to basically report different levels of confidence intervals. So I'm going to check 95% confidence interval. So here, then I have 95% lower bound of confidence interval and 95% upper bound or higher bound of the confidence interval. So basically that these three lines, the last three lines, shows that on average 67.4 customers have left the system, and this number, the average number of customers that have left the system on a specific day, on Mondays for example, can vary also between 62 and 72, almost 72.8. Okay, so these confidence intervals are good and should be reported because they can give me a sense on how much I can trust this average. Because if I report an average and then I report a confidence interval, a 95% confidence interval that is not too wide, that means I can trust this average. If I'm going to plan for something, if I'm going to hire a bunch of people who are going to help me as clerk on that day, I can trust on how many people I will get in that specific day, because that number, that average, is not in a wide confidence interval. So it's on average 67, but it may get to 62 or 72, and that's fine as well. Okay, so this is a good reasonable confidence interval, for example, for this average. So we can then report the average, report the confidence interval, and let the managers decide how they want to proceed. Okay, the next thing I want to talk about is the concept of confidence interval and how we can make these confidence intervals narrower. Okay, so let's see one more time what these numbers mean: the average, lower bound of confidence interval, and higher bound. Okay, so the average just means that if, as I said, you are asked to report how many customers exit the system on a specific day, let's say on Mondays, we take 10 samples of the Mondays and then we report, yeah, on average about 67 customers get the service and leave on Mondays. Okay, but every time I take a sample, if I repeat it one more time and take sample for another 10 days or another 10 Mondays, if I take a sample of size 20, 30, or as I said, even if I take another sample of size 10, then the values of the sample may be different, and as a result, the average will be different as well. So now the question is that what are we going to report? Should I report the results of this sample, average of this sample, or should I repeat another sample? Should I repeat a bigger sample, and so forth? So that's why the confidence intervals are reported, because basically here we say that okay, I took a sample of size 10 and on average about 67 customers have left the system, but if I repeat this over and over and I take different samples, I expect the average of the customers that leave the system on one day, on a Monday, to be somewhere between 62 to about 73 customers with 95% confidence. So with 95% confidence, the average of people who get the service on Mondays falls somewhere between 62 to about 73. Okay, so basically that's what these numbers mean. So that's why I said if our confidence interval is narrower, that's a good one. That means that we can trust this average that we have obtained. But if I report an average and a wide confidence interval, that's not good, because then, yeah, this is the average of my sample, but the confidence interval, a wide confidence interval, shows that this average can vary from this lower bound to this upper bound. And if that's really wide, so what does that really tell us? Not much. Okay, so a lot of time happens that we are asked to report a confidence interval that is narrow so that we can trust this average that we are reporting. Okay, so then the question is that how we can make this confidence interval narrower. Okay, And that's what I want to talk about. So let's look at the formula that we are using for the confidence interval. Okay, so if you remember from the confidence interval concepts that you had in the statistics class, so this is the formula for confidence interval. Obviously, the average of my sample is in the middle, and then average plus z of alpha over 2 multiplied by sigma over square root of n gives me the upper bound or upper limit, and then the lower limit is average minus z of alpha over 2 sigma over square root of n. So sigma is just the standard deviation of my population, so the standard deviation or variability among all samples, and n is just the size of the sample, and z of alpha over 2 is basically the number we get from the z table based on our confidence level. Okay, so the sigma basically shows the standard deviation of the whole population, meaning that if I had the power to get data of all possible Mondays for this restaurant, then I look at the variability among them and calculate the standard deviation. That would be sigma, but we don't have that power, right? We just can get a sample of size 10, 20 or so from the number of customers that have left the system on a specific day, right? So if I cannot look at the whole population and I just have to look at the sample, then I have to use the standard deviation of the sample. And in that scenario, the formula changes to x bar plus t of alpha over 2 multiplied by s over square root of n. So instead of sigma, I will put s, and since instead of z of alpha over 2, I put t of alpha over 2 and n minus 1, and n minus 1 is the degree of freedom of this t distribution. Okay, so so the formula for upper bound and lower bound will change to these values. Okay, so now the question is that, okay, what is the size of the interval here? So if you go back to the previous scenario, we see that if I have the average and I have to add this value z multiplied by sigma over square root of n to get to the upper bound, and I have to deduct this value to get to the lower bound, then the size of the half of the interval is basically this value, this constant is z multiplied by sigma over square root of n. Okay, so that's basically the size of the half of confidence interval. Okay, so x bar is the middle of the confidence interval, x bar plus this constant is the upper limit. So if I deduct the upper limit minus the middle point x bar, z of alpha over 2 over multiplied by sigma over square root of n is the length of the half of interval. If you calculate the length from the lower bound, the half of the length considering the lower bound, that's the exact value you will get to. Okay, so the size of the half of interval, if we use this formula, it's z multiplied by sigma over square root of n. If we use this formula also, it doesn't matter. So still the size of the half of the confidence interval is t multiplied by s over square root of n. And I use the notation E just to show the size of the half of interval. So that's just a notation that I'm going to use in the formula. So that's not very specific. Okay, so the size of the half of interval is t multiplied by s over square root of n. So as I said, a lot of the time it happens that we get the average, we get the upper bound and lower bound, but we are asked to somehow reduce the size of the confidence interval. So the question is that how can I reduce the size of the confidence interval? Obviously the average is average, we can't change that. So this is the constant that we are adding to the average, and this is the constant that we are deducting from average to get to the upper bound and lower bound. So obviously if I want to change the size or the length of the confidence interval, I have to somehow play with this constant, or that I call as E, or the size of the half of confidence interval. Okay, so this E, that again, which is equal to t multiplied by s over square root of n, is what I want to play with to see how can I reduce the size of the half of confidence interval, because if I can reduce the size of the half of the confidence interval, I can reduce the size of the confidence interval, right? So I can achieve my ultimate goal. So the question that I have is that what I can play with to reduce the size of the interval. Okay, so S is the standard deviation of the sample. It's not a number I have control over. So I just get a sample, whatever standard deviation of the sample is, that's the value I'm going to use for S. So I have no control over this number, no over S. So T, if I want to reduce the size of the confidence interval, or if I want to reduce E, or if I want to reduce the size of the half of the confidence interval, if I want to reduce E, I have to reduce T, okay? And reducing T requires me to reduce alpha over 2, or my confidence level. But I don't want to change my confidence level. If I construct a confidence interval of 95% confidence, I still want to keep that confidence level, okay? So I don't want to reduce my confidence level in the interval I'm going to develop just to be able to reduce the size of the interval. So then I'm not going to play with T as well. So the only thing that I can play with is N, or the size of the sample, or the number of replications. And as you can see here, for E to decrease, N has to increase because N is in the denominator. So that basically means if I want to reduce the size of the confidence interval that I'm reporting, I have to increase N, or increase the sample size, or increase the number of replications I have. Okay, so then the question is that, okay, what is the right value of N? If I know what I want to be the size of the half of the confidence interval, what is the right sample size or right number of replications that can give me that desirable length of the confidence interval? Okay, so if from this equation, I can calculate the value of N, and this is the formula that I'm going to use for the value of N. So N equals to T multiplied by S over E, where E is the desired size for the half of the confidence interval, and this whole thing to the power of 2, that gives me N, or size of the sample, or number of replications. Okay, so let's go to our example to see how basically this formula is applied to our example. Okay, so here, if you remember, I calculated the average. I calculated the simulation calculated for us automatically the lower bound and upper bound for the number of customers that exit the system, the lower bound of confidence interval, the upper bound of confidence interval. I can also see the standard deviation of all these numbers, all these replications, or all these samples I have obtained. If I go to the left side of the output view, is one of the things that I can check is a standard deviation. If I check a standard deviation, you see automatically a standard deviation row is added here. So then all I need are these 4 last lines. I need to know the average, the standard deviation of all these replications or samples, the lower bound of confidence interval, and the upper bound of confidence interval. So I have put all these numbers in an Excel file so that we do the calculations together, and you see how we can get this. If I want to reduce the length of the interval, if I want to have a narrower confidence interval, how should I increase the number of replications that I'm going to get? Okay, so here basically is the average we just saw on the output viewer. Here is the lower bound, and here is the upper bound. Okay, so the confidence interval length basically is upper bound minus lower bound. That's what I have put here, C5 minus C4. Okay, so the upper bound minus lower bound gives me 10.8, or almost 11. That's the size of my confidence interval. Okay, so now let's assume I want to get a new value for the size of the confidence interval. Okay, so I want to get a new value for the size of the interval, and I want to come up with a confidence interval that is the half of length of the previous interval. So I want it to be a lot narrower. How much narrower? I want it to just be 50% of the previous interval. So I want the new length to be the original one multiplied by 0.5. I want the new interval to just be 50% of the original one. Okay, so that means the new interval that I want, the new upper bound minus lower bound, should be 5.4. Okay, so that's the new length for the confidence interval that I want to construct. So that means that the new value for confidence interval half length. Okay, so the half of the length of the new confidence interval is going to be just this value divided by 2. Okay, so that's also the value of E. If you remember, based on the formula that we had, that's the value of E. So E, or the half of the size of the new confidence interval that we want to construct, is 2.7. Now the question is that how many replications I have to get to give me this new value for the size of the half of the confidence interval, or this value for the size of the whole confidence interval, new upper bound minus new lower bound. Okay, so going back to the formula, I need to know T, I need to know S, and I need to know E. Okay, so to be able to calculate T, if you remember, our confidence level was 95%. So alpha over 2 is 1 minus 95 0.95 divided by 2. Okay, so basically alpha over 2 is 1 minus 0.95 divided by 2. Okay, so that's 0.025. Okay, so the question is, and we also know the degree of freedom n minus 1 is the size of the sample minus 1, that's 10 minus 1 is 9. Okay, so the question is that how can I get the T value corresponding to this alpha over 2 and n minus 1? So I want to get a T value where the size of the T curve on the right side is 0.025 and the sample size is n minus 1 or 9. Okay, so we have to go to the T table. So this is the T table that we have. So first of all, for always when you use the T tables, look at the graph and just make sure the alpha that is shown on the top is the area shaded on the right side. Okay, so that's the shaded area on the right side, and that's exactly what I want. I want this area to be 0.025. Okay, so that's this column. The degree of freedom that I'm looking at is 9. Okay, so if I look at the degree of freedom of 9 and the area of 0.025, the number, the T value that I'm going to use is 2.262. Okay, so 0.025 is alpha over 2, then the area that I want on the right side, and the degree of freedom of 9, that's 2.262. Okay, so the T value then is 2.262. Okay, so then the N, or the new size of the sample or new number of replications that I need based on the formula is T. I have to multiply T by confidence by the standard deviation. So just let's go back and look at the value of the standard deviation. So standard deviation of the sample is 7.55. So let me go here and write the standard deviation of the sample S, which is 7.55. So then N, the new size of the sample or the new number of replications is, based on the formula that we had, T multiply by S divided by the E, or the new value for the size of the half of the confidence interval, and all of these to the power of 2. Okay, so that shows that the new size of the sample or the new number of replications should be around 40 or so. So let's say 41 if we want to round it up to the top, to up. So that's about 40 or 41 replications to give us this desired length of the interval, or this desired value for the size of the half of interval. Okay, so now if I go back to the simulation, and if I just run this for about 41 replications, so let's see what do we get. Okay, so I still get the average. So I want to show the standard deviation, and I want to show the 95% confidence level. So as you can see now, the average is about 65 customers, and it's the 95% confidence interval I have constructed is between 63 to 67. So the size of the confidence interval is about 4 units, and that's pretty much close to what we wanted. Remember, I wanted the size of the confidence interval to be around 5, but now the confidence interval I have constructed is even less, which is even better. Okay, so if you happen to see that the size of your confidence interval, the new confidence interval, is just a little larger, just repeat these numbers again. You have a new sample, a new value for standard deviation. The new value for sample size is 40 or 41, and so just repeat this formulation for n, given these values that you have for the standard deviation, and given the new value for t, because the size of the sample has changed, obviously your degree of freedom has changed, so your t will change. So just repeat the formula to see what would be your new value for the samples, for the sample size. And again, I say to repeat this one more time, because remember here I'm using S as an estimate of the standard deviation for the population, for sigma, right? I don't have sigma, so as an estimate I'm using S instead of sigma. So that's why the number we get in terms of number of replications will definitely get us closer to the confidence level that we want, or maybe even give us something better in this scenario, or give us something that is just a little larger than what we want. And if that's the case, just repeat the whole scenario one more time with the new values for S and new values for T, and that gives you a new value for the number of replications that you have to run, and that gets you closer to the confidence and to the size of the confidence interval that you want to construct. So right now I come up with a new average, and I constructed a confidence interval that is a lot narrower, and that's a lot more reliable. So that means I can trust this average a lot more. So if I need to do any planning based on how many customers I get on a specific Monday, then I can trust this number a lot more than before.